Welcome to this virtual presentation titled Is Your Test Data as Agile as Your Developers? My name is Kai, and I want to look at agile software development and how it affects the way we think about test data and test environments. The first half of this presentation involves concepts that are not really specific to any database system, so it doesn't matter if you use DB2 for ZOS, DB2 for LUW, or even a non-DB2 system. There are a couple of things in the second half that are mainframe specific, and that's simply because the mainframe DB2 is the platform I am most familiar with. But it doesn't mean you couldn't do similar things on other systems. More specifically, I'm first going to talk a little bit about the new challenges to our test environments and the data inside that arise from the ongoing shift to agile development methods. It turns out that the concept of continuous integration that is a key part of agile development requires a large number of small test beds, so we will be talking about how to create those and how to populate them with very specific data. We will look at the expert knowledge that is required to identify exactly what data from which tables is needed based on the requirements of a test case, and how you can make that knowledge available to more people in your organization. In addition, we will look at how to efficiently clone very large environments, because it turns out this is something we still need to do. And I'm going to wrap things up with a couple of final thoughts on the topic. Over the last 15 or so years, there has been a noticeable shift in how software is developed. People and companies have moved away from what we might call traditional development methods to more modern approaches. Not everybody may be deeply familiar with development methods such as Scrum or the concepts of agile software development and continuous integration. But I think it's safe to say that everybody has at least heard those terms before. According to market research company Forrester, the percentage of businesses that actively use agile development methods has risen from only about 14% in 2005 to 95% in 2016, which basically means that everybody is using agile software development to some degree nowadays. One of the key differences with methods like Scrum is the way software is tested. And since this is a conference about database systems in general, and DB2 in particular, we are going to assume for a moment that we are looking at an application which stores the vast majority of its data in a relational database system, in other words, DB2. Let's take the well-known waterfall model, for example. To put it simple, first the requirements for the finished software product are defined. Then development begins. After development finishes, the test phase begins. It is at that stage where the application is executed against data in a test database. The test beds are typically large. They contain all the data that is needed for any of the tests. It could be that the test bed is a copy of a production database, hopefully one where personal information has been removed. There is also a very well-defined transition between the different phases of the development model. Once programming is done, a handful of test beds are prepared, and off we go. In agile development, things look different. Programming and testing happen in parallel. Very small pieces of code are tested individually, and for these tests, very specific pieces of test data are required. Tests run at least every night, but more likely multiple times per day. And that means that dozens or hundreds of test beds need to be created, populated, used, and then cleaned up. Now, that does not mean that we don't need the larger environments anymore. We still want to be able to do performance tests, for example, where an application needs to process 10 billion rows, because if we have implemented a time-critical part of the application as an algorithm with a bad complexity, then we're not going to see this when we run the function in question against 10 rows. So in order to judge if not only the results are correct, but the runtime behavior of our application is acceptable, we need those big test environments, probably by creating a clone of our production system. So we need both, the big and the small. And perhaps counterintuitively, creating the big environments is relatively simple from a technical standpoint, but creating these small environments can be a bit of a challenge. When we look at the test environments that are typically being used, we almost always see that large amounts of data are moved around using the unload and load utilities. These are utilities that come with DB2, so they are often the go-to solution for every task involving data movement. Unload and load are primitive tools. They only move data. There is nothing built in that would generate or compare structures, so additional tools are required just for that. Data is taken either from production tables or from image copies of production tables, although to be fair, you can of course run unload once and then keep the data around for a while, and then with every load you do, you can get your target tables into their previous states, which is useful. But this will require a lot of temporary space, and that is also why we usually see that people create only a few test environments, which testers then have to share. Sometimes we see people replace the normal unload utility with a slightly faster alternative called high-performance unload, but this is really just putting lipstick on a pig. The slow part is the load, so you won't be able to get more than about 20% overall performance improvement when you look at the whole process. From the point of view of someone who has to test software, these environments are not ideal. First of all, they're not being refreshed frequently enough. Test environments that are months or years old are common. And that means that the data in these environments is old and stale, and that can be a problem for testers. Think of an application that keeps track of invoices. When the test data is half a year old, then all open invoices are overdue. No new invoices have been written in months, no new orders have taken place, and that does not represent what the application normally sees in production. Testers may also have to share the same set of test tables, and that can mean that they step on each other's toes. In other words, running one test can influence the results of another, and that is never a good thing to have. From the perspective of a DBA, the refresh process is tedious. If problems occur, it can take a while to sort things out, and then figure out how to continue without starting over. These jobs consume a lot of CPU cycles anyway, so going back to square one is not always a good idea. So what do we really need to support agile development processes? When you look at a typical build process, there is of course a build phase where the source code is checked out from a certain branch in a source code repository or version control system, such as Git. That source code is compiled and an executable application is built. Part of the build process is also running tests, and a lot of them. In fact, testing often takes longer than compiling because there could be hundreds of different scenarios that the application has to correctly process. Some tests do not require any external artifacts. Self-contained functions can easily be tested with unit tests that supply different input values and then check if the math was done correctly. But more often than not, a test requires the application to interact with data that is stored externally. Could be a flat file, could be a database. For those test cases, the data that the application works with needs to be prepared. Every time the test runs, and this could be several times per day, there must be some sort of process that makes sure the application always finds the exact same data to work with. So what we need for running a large number of automated tests are small amounts of data. It is just not feasible that every small unit test runs against a multi-terabyte database. First of all, response times from the database are usually better if the tables are small. And that's even when all the queries have been optimized and all indexes are in good shape. Second of all, initializing each testbed would simply take too long if it were a full copy of a large environment. We want something that can give us the data that is needed for a specific test or test suite in seconds, not hours. As a result, we are looking at plain old SQL statements to insert very specific data into the tables that our tests will use. Nevertheless, we still need those large environments. Not for the unit tests that run during the build process, but for things like performance tests and acceptance tests. In these tests, you absolutely want to have as much realistic data as possible in your tables, ideally a clone of a production system. Otherwise, you would not be able to measure performance or to verify that the application is actually able to deal with all the real data that you have in your production. As mentioned before, the small environments are not a replacement, but an add-on to what you currently already have. Simple scripts that consist of a number of insert statements are not sufficient to populate test environments for your agile development process. In theory, if you were always able to start with an empty set of tables, running a long list of inserts might work. But in practice, you must be able to merge data into tables that are not empty, or to insert 5 copies of the same test case under different IDs. And this is something you need to be able to do on demand. That's because unit tests are small and there are many of them. It takes only a minute to create a new unit test for an edge case, and when that happens, you don't want to sit down and create a new insert script. You want a process that can automatically determine which rows from which tables are needed after it is triggered with parameters. These parameters could be something simple as a list of keys, or something more complex such as 10 random insurance policyholders that had 5 or more claims over the last 12 months. Another reason why simple scripts are insufficient is because applications sometimes use database tables not just as big containers to store relational data, but to store metadata instead. It is very common that tables exist which, for example, keep track of how many valid rows some other tables have. These values must be updated correctly after modifying the data in other tables, and at that point you need program logic. Now, is this something that could better be handled with views or materialized query tables, sequences, or maybe triggers? Absolutely. But the reality is that products often limit themselves to the smallest common feature set that is available in all supported database systems, and it is this constraint that results in tables being used in the way I described. So we have decided that we want to populate a small test bed. We want individual test cases, and the main challenge here is that a single test case can consist of hundreds or thousands of rows, and these rows can be spread over hundreds of tables. This is one of the consequences of having a relational database to store business objects. A single insurance policy, for example, is not represented by one row in one table. It is a complex web of rows, some of which represent the insurance policy itself, some of which represent the policyholder, his or her address, the claims and invoices that are related to the policy, the list goes on. Fortunately, we have foreign keys in our database. Well, sometimes we have foreign keys, that is. A lot of applications simply don't use them for a variety of reasons. Personally, I think that foreign keys are one of the main building blocks of a relational database, so you should use them wherever and whenever possible. But in practice, there are lots of applications that handle the internal relationships between rows in different tables themselves and don't use the built-in mechanisms of the database. But are foreign keys really the answer to our problem? It turns out that they are helpful, but they are not enough. Foreign keys tell us a little bit about the semantics of our tables, but they do not really tell us what an application or a test case needs, and, just as importantly, what it doesn't need. Here's an example. In a very simple application, a contract might be represented by a row in the contracts table, and an invoice is represented by a row in the invoices table. An invoice always belongs to a contract, and a contract can result in 0 or any higher number of invoices. So we would model our tables accordingly. Contracts is a parent table of invoices. But at the same time, our application also keeps track of when details of an existing contract change. So we have another table, let's call it contracts changelog. And every row in that table has a timestamp, a contract number, and information about what exactly was changed and who changed it. It allows us to keep track of the history of a contract. From the database's point of view, contract is a parent table of contract changelog, just like it is a parent table of invoices. But in a test scenario where I'm testing a program module that prints invoices, I'm only interested in the contract itself and the related invoices. I couldn't care less about the history of the contract details. This means that the two child tables have a different meaning for me. I need the rows from invoices, but I don't care about the rows from contract changelog, and it would be faster and more space efficient if I could skip that table. In a big application, those tables that keep track of changes can become very large, so why waste time copying a million rows from that table if I'm not going to use them? In a way, what we really need is to be able to define a path through our tables. We need to be able to say, start with a contracts table and grab all the rows based on the initial list of contract numbers that I gave you as a parameter. Then go to the invoices table and grab all the rows that belong to any of the extracted contracts. Do not go to contracts changelog. I'm not interested in that table. Let's have a look at an example, what it really means to copy test case data in a way that makes sense for a developer or tester. As our sample application, we will use vTiger 7.1, which is a CRM system that many companies use to keep track of their customers, the business opportunities, and related information. vTiger is an open source application and it's very straightforward, pretty much what you would expect from a customer relationship management system. Maybe you're using vTiger and you're developing a plugin of your own that helps you better understand your sales process. You might be in a situation where you need to test a piece of code that you have written that somehow processes all contacts that belong to a certain organization. It could be a module that generates a report that relates all those contacts to the total worth of all sales opportunities that you were able to generate. To test this, you might say, I need an organization that has at least 200 contacts attached to it, and for my test, I need all those contacts and sales opportunities that are related to those contacts. Here's a peek at what vTiger looks like. The browser-based front end allows you to browse the organizations that you're doing business with and the contacts that are related to these organizations, and of course a lot of other things. Behind the curtains, vTiger stores its data in a relational database system. When you install the software, it will create its tables in a database of your choice. The vTiger schema consists of 523 tables in total. In a typical vTiger system, most of these tables contain data, but some of them could also be empty. It depends on what parts of the CRM system you use and what parts you don't use. The structure of those tables is partially documented, but you can look at the foreign keys in order to find out how these tables go together. There is one table where the so-called accounts are stored. An account in vTiger is simply an organization with its name and address that you have entered into the system. This table contains one row for each of those accounts, so it's a good starting point. Looking at the foreign keys that exist in the database, it turns out that 97 tables are connected to the accounts table, either directly or indirectly. After some analysis, we are left with 14 tables that are relevant for us. In other words, those are the tables that are required to represent accounts, contacts, and business opportunities in the vTiger system. The other tables may somehow be related to an account, but they are of no interest to us. In addition, the vTiger application also has one central table where everything that has ever been entered, whether it's an account, a contact, an invoice, a delivery slip, or anything else that can be entered into the system, has one row that, among other things, assigns a system-wide unique ID and also a label that is indexed for fast searching through all the objects inside the system. And finally, there are tables that contain meta information about other tables. For example, one table contains the total number of contacts that exist in the system. For new entries, the system looks up the number of rows, adds one, and that will be the new entity-specific ID because, well, of course we have globally unique IDs, but we also have IDs that are only unique within their own table. You could argue that you should not use tables in such a way, and that this information should be obtained by a view that counts the rows, or maybe by a sequence object. And you would be right. But maybe this is a vendor product that you download and install, and you have to live with those tables. You cannot change the way the database is designed. And even if it's an in-house product, that part of the table design was probably decided on years ago, and you don't want to completely change the entire application backend and the way data is stored in the database just because you're adding a small feature and now you need to test it. Here's an image that visualizes the table that we need to look into when copying a single account, including its contacts and business opportunities. The yellow rectangle represents our start table. And from there, we have to define which tables to look at next, in which order, and maybe also if we need to sometimes go back to a table that we already have visited in order to grab additional rows. For example, there is this central table that I mentioned where everything that exists in the CRM system has a row. This means that there is a row for our organization, and that row has a unique system-wide ID. And there are also rows for every contact that works at that organization, and every contact also gets a unique system-wide ID. But of course, we have a table just for the organizations, where our organization also has a row, and a table just for the contacts, where each of the contacts has a row. As a consequence, we need to grab the organization first, which means grabbing the row from the organizations table and also grabbing the row from the central table. But then we discover that there are several hundred contacts associated with that organization when we look into the contacts table. We grab those, and then we need to revisit the central table and also grab the rows that represent the contacts from there, because the system always needs the entry in the central table and also the entry in the entity-specific table. It's not exactly a circle, it's more going back and forth until we have everything that we need. When everything is said and done, in order to copy that one organization that we were interested in, we had to copy hundreds of rows from 14 different tables, and to find them all, we had to follow the path that somebody else had laid out for us, somebody who knows the application and the way the data is stored in the tables. So we have a lot of complexity in the relationships between the tables that store our application's data. But there's more. Every application of a certain size has ways for users to customize things. It can be something very simple, such as end-user settings for a browser front-end. That is something we don't really care about during our automated tests. But it could also be something that directly affects us. Most applications allow us to heavily customize the fields that belong to the objects, such as, in our example, the insurance policies or invoices. They usually also allow us to define relationships between objects on a level that is above the database. So there is a layer of abstraction. We could call that a middle tier, which is of course also stored in database tables. It is the information from the middle tier that makes the raw data in other tables usable for the application, and it allows the application to enforce internal constraints. For example, if we are looking at a health insurance policy, then the subject of insurance is the policyholder. But if this is an auto insurance policy, there needs to be an associated vehicle somewhere, and this is a separate object. It is also stored in the database, and there is this relationship that the auto insurance cannot exist without it. This middle tier of meta information must also be replicated in order to properly test certain aspects of an application. Since this is information that must exist exactly once, it cannot be missing, and you cannot have duplicate or conflicting information. It needs to be handled differently from normal data, and we must be able to replace or delete this type of information from our test beds. So far, we have mainly talked about the technical aspects of providing data for agile testing. But there are organizational aspects as well. Even in the best-case scenario, where all the information about the tables, their contents, their relationships, and all the meta information is available, it is usually concentrated on a small number of people. Not every developer and not every tester has this very detailed knowledge, and that is often because they usually do not work directly with the database. They work with abstract objects in the context of the application. As a consequence, their requirements for test data is more along the lines of, I need 5 policies with the following criteria, and not a detailed description of all rows from all tables that should be copied. To translate between those two worlds, we need someone who can create a model of the application in regard to the underlying database, including this route description that we talked about earlier. These translators, or modelers, therefore make their special knowledge available to the masses, the developers and testers, that is. The ability to use parameters to trigger these test data provisioning processes also allows developers to try something out real quick, so that, for example, they can easily grab edge cases for testing. This is sometimes called exploratory testing, where tests are designed spontaneously based on what the developers think needs to be looked at. So for that, you need some sort of front end that gives developers the ability to order test case data, and then an automated background process must build the environment and fill it with the test cases that were requested. Exploratory testing is important, but it's not the main field of application. Much more often, the test data provisioning processes are triggered by other processes, and in this case, this is often a tool such as Jenkins, which orchestrates the entire build process of an application. The Jenkins process should therefore include steps to create the test bed, populate it with the required data, then run the tests, and then also delete the test beds once they are no longer needed. The de facto standard way for two applications to communicate is REST, so that Jenkins can send a simple HTTP request in order to trigger the creation of the required testbed. As a consequence, when you design your test data provisioning process, make sure that it can communicate with the rest of the world. You need to be able to accept requests from a process like Jenkins, and you need to be able to communicate back if the data movement was successful or not. In addition, you should be able to write some form of log where it's clearly visible what data movement was done, at what time, between which environments, how long it took, and so on. This allows you not only to do a visual verification of what was done, but also to comply with auditing requirements, which is a common thing when access to production or production-like data is involved. Let's say your process is ready to be used and it's nicely integrated into Jenkins. The next question is then, what will be the data source for this process? Since a process that moves small amounts of data is built based on SQL, it will run normal select and insert statements. So it is tempting to connect this process to a production database and get test data from there. But that is not a good idea for several reasons. First of all, you should not just be running random select statements against production tables. Remember that we have created a path through the tables, and sometimes our process extracts rows from a child table and then descends to dependent tables. Sometimes the selection criteria for those dependent tables do not reflect typical production workload, and this can cause the database to perform things like full table space scans. This does not really affect our test data provisioning process, except for the fact that the data is retrieved very slowly. The real problem is that this can affect the real production workload. If the production system gets slowed down because our query caused the database to bring tons of pages into the buffer pool that are required for a full table space scan, you have a problem. Response times of critical applications can suffer, and this can happen at any time of the day due to how continuous integration works. Of course, there are also authorization problems. Not every tester should be allowed to grab data from a production database, particularly because that data can contain personal information. Typically, access to production is tightly controlled, so going there in order to get data might not even be an option. And even if it is, you still should not do it. Finally, a production database is something that is constantly changing. And as a consequence, if you run the same test data provisioning process twice, you might get different data, and that is something that makes tests much less useful. If the table data on which a test works is different for each execution, then if a test fails, you cannot really be sure if the problem was a recent code change, or if you are seeing a problem that has existed for a while, but the application just never processed that specific piece of data. Ideally, the source environment from which our test data provisioning processes can take their data is an environment that does not change. And this could be a clone of a production system that is maybe refreshed once a month. Obviously, this would be a large environment, since it's either a full copy of everything that's in production, or maybe a clone of a subset of the tables that exist in production. The question is, how can you create such an environment without affecting the availability or the performance of the production environment in a negative way? Such a copy of a production system is often called a golden copy or master copy. If a test environment needs real data, this will be the system where the data comes from. You might also hear the term pre-production, and this is essentially also a direct copy of a production system, but in a pre-production you also have the full application stack installed, and it is the environment where you work with the next version of an application that is in its final stages of development before it gets promoted into production. So let's call our environment the golden copy. The idea is that you have an environment that looks like the production, but it is not the real production. And that means you are free to run queries or utilities without disturbing the real production environment. And it's also an environment that doesn't change. Under normal circumstances, nobody is actively working with this environment, so the contents of the tables does not change. And this is very useful because it means that every time you take data out of this environment, it is in the same state. Let's say you create the pre-production environment on the 1st of every month. Then, for the rest of the month, Whenever somebody copies test data from this pre-production, they're essentially resetting their test environment to the state of the production system on the first of the month, and the tests can run over and over again with the same data. Now, obviously, when you use an environment like this for acceptance tests, this will change the data in it. It would be very unusual for a large test suite to only read data but not insert, update, or delete any. So some people actually have multiple clones of their production systems, either full clones or partial clones, so that some can be used for testing and some can be used as a data source to populate smaller environments. But the testing that is done here is not your average unit test that is run by a developer or by an automated build system. These are the performance tests that need to work with hundreds of millions of rows. In other words, large tests that take hours. And that brings up another important aspect of these environments. By definition, a clone is a one-to-one copy of a source system. So by default, the data in the clone will be identical with the production data. All the real names, real addresses, real email addresses, real bank account information will be there. And that means you have to make a choice. Either you leave the data as it is, because that makes acceptance tests much more valuable, but if you do that, you need to severely restrict access to that pre-production. Somebody who is not allowed to access production tables should not be allowed to access a clone of the production either. Or you modify the data in that pre-production so that personal information is removed. The finer details about data masking go beyond the scope of this presentation, but it should go without saying that data that is used for testing purposes should typically not contain any personal information. You can choose to apply data masking to a pre-production system. It can be a bit tricky because this is typically a very large environment, so masking all the data can take a while. But if you can do it, then you can use it as a data source for smaller test environments, and you don't have to worry about data masking in those environments ever again, because the copy processes that populate them already read from a masked source. The best way to create a full clone of a production DB2 subsystem or a production data sharing group is to make a hardware-assisted copy of all the volumes that belong to DB2. Every storage vendor has tools that allow you to copy an entire set of volumes, and this could be hundreds or thousands of volumes, to a set of target volumes. Now you could make these copies using standard ZOS mechanisms such as ADRDSSU. But what makes these hardware-assisted copy mechanisms unique is the fact that they are able to create a point-in-time copy of the entire set of volumes. In other words, if you clone 1,000 volumes using such a mechanism, then each of the target volumes will look exactly like the source volume at the point in time where the cloning process was started. Let's say you make the clone at 2 in the morning. Physically, it takes a while for all the data to be copied, but logically, such a clone is instantaneous, and you can start working with the target volumes immediately. The hardware makes sure that the operating system sees the cloned volumes as independent volumes and can use them without limitations even as the physical data movement is still going on in the background. The big advantage of this is that it allows you to make a full clone of your entire production DB2 without stopping it. There is no interruption at all. However, you need to be aware that these cloned volumes are not directly usable. You need to implement a process or a piece of software that turns these cloned volumes into an independent DB2 subsystem. There are red books available that give you detailed instructions on how to do this, and there are also vendor tools on the market that make this process very easy. Once you implement this, you have a complete decoupling of your production system from everything test-related, and you will have exactly one process that accesses production for the purpose of getting test data. Obviously, you need quite a bit of disk space when you want to make a full clone of production, but the benefits usually make it worthwhile. And keep in mind that a clone of your production DB2 requires very little maintenance, basically no maintenance at all. Since it is a system where nobody is really changing anything, there is no need to make image copies or to run reorg. It is a perfect point-in-time snapshot of your production. Creating such a full clone is not difficult, but there are a couple of things that you need to set up inside your COS system. Fortunately, this is something that you only need to do once, and afterwards you can repeat the cloning process as often as you like. or rather as often as it makes sense within your test data management concept. You need to create the subsystem definitions for DB2 itself and for the log manager, otherwise the operating system does not know that there is a new DB2 subsystem that can be started. You also want to make sure that you create separate SMS classes and the corresponding ACS routines. Even though the clone is a system that people usually don't work with, you might want to add or change a thing or two after making the clone, and if new datasets are created in that process, either log datasets or page sets, then you need SMS to pick them up and assign the correct classes. Then you need to configure a thing or two regarding VTEM and TCP/IP so that people will be able to connect to the new DB2 subsystem. You also want to use RACF profiles to protect the cloned datasets, which will either have different dataset names or be cataloged on a different system. Since the clone has all the real data from production, you typically want to make sure that people who cannot access production are also unable to access the clone. And finally, you need to assemble a new set of zparms, because that is also a place where you will find references to dataset names, such as the prefix for log datasets or for the page sets of the catalog. Now, this may seem like a lot of work, but remember that you only need to do it once. And by the way, these things are not specific to making a clone of a DB2 subsystem. You would need to do the exact same things if you were in the process of setting up an entirely new empty DB2 subsystem. Once the initial setup is done, though, the process becomes very simple. You make a point-in-time clone of all the volumes that DB2 stores data on, and you use a hardware-assisted tool to do it. An automated process then renames the volumes themselves, the datasets on them, and certain information in the DB2 catalog, directory, BSDS, and active log. Then you start the new DB2 subsystem. There is one small problem, though. Let's say that we have copied the volumes at 2 in the morning, which means that everything on the target volumes looks exactly as it did on the source volumes at 2 a.m. But what if there were open transactions at 2 a.m.? A large update operation that started at 1:58 and was still running when the volumes were cloned. At first, you might think that if something like that happens, you end up with inconsistencies in the target system. But it turns out that this little problem is not really a problem at all. Since the cloning process also involves the volumes where the log and the BSDS is stored, all we need to do is make a warm start of the target DB2, and it will immediately detect that it was not shut down properly. It was cloned from a set of hot volumes after all. And what does DB2 do when it starts and detects that it was not shut down properly? Well, that's right, it starts going through the BSDS to identify the latest checkpoint, and then it applies log records up to the current point in time in order to make sure that all the transactions that had been committed at the end of the log are correctly applied to the page sets, and all transactions that were not yet committed are rolled back entirely. So the DB2 subsystem makes itself consistent, and there is nothing that we need to do. When it's done, the target contains all changes that were committed before 2 a.m. and nothing that was uncommitted. Now, we have seen that not everybody wants to have a full clone of their production DB2, or maybe they want one, but for some reason, whether it's DAST space or something else, they cannot create one. Maybe you want multiple large environments, but not everybody needs everything. And for those cases, it is also possible to make fast copies on dataset level. This allows you to make partial clones. So for example, you could only copy those tables that contain the master data that everybody needs, customer records mostly, and then in addition to that, every department gets a full copy of the tables that are relevant for them. This is something that you cannot do by cloning volumes anymore. In this scenario, you need a tool that is able to create and compare sets of tables and then copy the data quickly on vSAM level. This is also an area where unload load is used in many companies, but if the amount of data becomes too large, then these standard DB2 utilities are no longer feasible. There are vendor tools on the market that can be used as a drop-in replacement for unload load, but are much faster. In addition, some of these tools can make copies of page sets while they are being used by a source DB2 subsystem. And this can be extremely useful if your source is a real production system and you want to make a copy of some of your tables, but you cannot stop them for the duration of the copy process, but still want consistency. The DB2 log contains all the required information, but again, to exploit that, you will need a specialized tool because neither unload load nor DSN1 copy will use the information on the log. Tools like these are also usually able to rename objects because they do not clone the entire DB2, including catalog and directory. Instead, they run DDL statements to create the target environment. And this also allows you to have multiple copies of the same data in one DB2 subsystem. You can simply use distinct database names and schema names, and this is something you couldn't do with a full clone. Using that copy that we have just made from our production system, we can now extract very specific test cases that are based on real production data. This ability is very valuable for testers because it allows them to quickly reproduce and hunt down a bug that has occurred in production. Like I said, you typically apply data masking to the copy of production so that testers do not get to see any personal information, such as real names or real bank account numbers. There can be situations where applying data masking removes data from a record that caused the bug in production. For example, if there is a contact with a name that contains a special character and the application is simply not prepared to handle that character. Data masking might replace the name with something else, and the problem might disappear in testing. This should not happen too often because in many cases, program errors are not triggered by the contents of the database fields themselves, but rather by the combination of rows from different tables and how they relate to each other. For example, an application might assume that an auto insurance policy always has an associated vehicle, but due to some weird things that happened in production, we ended up with a policy that has none, and that caused the application to crash. You can get this exact same situation in your test environment, whether the real names and real addresses are masked or not. At the end of the day, though, what you need is a combination of real production data, again, ideally masked, and a set of generated or handcrafted test cases that can be used to test if an application behaves correctly when handling edge cases or incorrect data, which doesn't even exist in production. Your test data provisioning processes therefore should be able to work with multiple data sources or data repositories so that you can cover all those cases. Obviously, tests should not interfere with each other. You do not necessarily need separate databases to store the data for each test, but you should make sure that the tables that are used by the different tests do not overlap. You could use distinct schema names, for example, so that running a test means that the schema is dropped if it exists, then created from scratch, then populated with a very specific set of rows, and then the test starts to run. And at the end, the schema is dropped again. That way, multiple tests can run at the same time without interfering with each other. On top of all that, you should keep in mind that larger applications are usually not monolithic. They are divided into smaller modules that communicate and exchange data. Let's circle back to our example of an insurance company. There could be a central component that verifies and validates postal addresses in order to make sure that no invalid addresses exist anywhere in the system. There could also be a module that manages the insurance policies, and since there are many different types of insurance policies with vastly different requirements and regulations, this is probably split into individual submodules, each of which handles one type. Then there is an application that manages claims, and obviously that has to be closely tied to the policy management, and so on. Crucial data might be spread across multiple different databases, and maybe even across different database systems. It is not uncommon that there is a master data file which is still using IMS because it has existed since forever and it's still used for names and addresses. There are invisible relations between those different systems that cannot be defined formally. Only the applications know about it. Remember when we talked about defining paths through the tables and how they are similar but not identical to foreign keys in a database? You can use that in order to jump into a different database and fetch related rows from there that the application will expect during a test. There are ways to access an IMS database, a vSEM KSDS, and even a flat file as if they were tables in a relational database, and you can use SQL queries in order to extract data. In general, if you have a lot of legacy applications and legacy databases to manage, things will get more complex and more difficult. Preparing small, meaningful test cases comes with a number of challenges. Many of them stem from the inability of relational database systems to grasp the semantics behind the data that is stored in them. Foreign keys are a useful concept, but they are not sufficient to fully represent the way that different rows from different tables are combined into business objects that are used by an application. But these objects are what application developers work with every day. Your test data management processes need to be able to translate between the object-oriented world of your applications and the relational world of your databases. And this is why you need to team up. There are many different stakeholders that are involved in the successful development of an application, and they all need to think about testing, test cases, and test data. The DBA cannot do it all alone. One of the consequences of adopting an agile software development process is that tests are executed very early in the process, and it is common knowledge that a bug in the code becomes more expensive to fix if it is detected late in the development process. But agile testing only works if useful test data can be provided quickly and reliably, and everybody involved in a project should support that with their knowledge and skills. This concludes the session. I hope I was able to shed some light on the new challenges that you may be facing as your application developers adopt agile software development processes. Feel free to contact me by email if you have any questions or would like to learn how we can help you implement test data provisioning processes suitable for integration into Jenkins or other automation tools. Thanks for watching.